The p-value. In publications, the statistical significance of a study is usually expressed as the p-value. It's the result of a study that's interpretable, as we'll describe later on in this episode. Even if you haven't heard much about the p-value, probably know that smaller p-values are better than larger ones. Let's find out why this is the case. The p-value indicates the probability of finding the observed or more extreme events when the null hypothesis is true. So what could such an event be? Let's use an example to demonstrate this. Assume you roll a die 5 times and get the number 4 on 3 occasions. Now you'd like to check whether the die is normal or whether it's biased so that the number 4 occurs more often. For this test, the p-value wouldn't only indicate the probability of rolling 4 3 times, but also of rolling a 4 on 4 or 5 occasions. Both events are more extreme than rolling the number 4 3 times. A smaller p-value implies that the observed outcome is unlikely. A larger p-value indicates that the outcome is not as unlikely. So what implications it has for our study? Let's go back to our episode on the null hypothesis. We learned to initially assume that the null hypothesis is true in a study. Our study data should then ideally refute the null hypothesis. Plotting the possible study results yields a bell curve in which we mark our previously determined result as a dashed line. In this context, we define a significance level on whose basis we can reject the null hypothesis. Beyond this value, we consider the probability of committing a type 1 error too high, so the null hypothesis is accepted. As a result, there are 2 rejection regions in the curve. So, from examining the significance level in the last episode, we know that our result isn't in the rejection region, and the study is not significant. Let's still examine the p-value of the study as well. So, according to our definition, where would the p-value appear in this curve? At the beginning of this episode, we stated that the p-value indicates the probability of observed and more extreme events occurring. Because we're performing a two-tailed test, the p-value is spread over both sides of the curve. The event to be examined is the mean change in the FEV1 value by 4 milliliters. So we're looking at the areas on both sides of the curve that represent this change as well as the more extreme results. The sum of the areas is the p-value. In practice, the p-value is calculated using statistical software and published with the results of the study. For our example, the p-value is 0.11. This value is now compared with the significance level, that is, alpha. In episode 10, we set a significance level of 0.05. This significance level means that the probability of falsely rejecting a correct null hypothesis is 5%, which is the probability of error. In court, the equivalent would be that 95 of 100 convicted individuals are indeed guilty, while 5 are actually innocent. In fact, it's debatable whether a probability of error of 0.05 would be adequate in this context. Depending on what's being investigated, a more stringent significance level can be set in advance. A level of 1% is also common. The p-value should then be equal or below 0.01 for the study to be significant. A significance level of 0.1% is also possible. The maximum p-value here should be 0.001. However, the significance level is usually not set higher than 5% for quality assurance. So a more stringent threshold results in a greater certainty that a false hypothesis isn't accidentally accepted, but it also results in smaller rejection regions, making a significant result more difficult to obtain. In our study, the p-value of 0.11, or 11%, is higher than the significance level. So as we already know, the study is not significant. Let's imagine that the change in the FEV1 value after administering the drug had been twice as large and averaged 8 milliliters. In that case, the study result would fall in the rejection region. The p-value would have been lower than the alpha value, and therefore the study would be significant. So in summary, a low p-value means that the observed effect is unlikely to occur when the null hypothesis is true. We conclude that it's not true, reject it, and accept the alternative hypothesis. In contrast, a higher p-value means that the observed effect is not very unlikely when the null hypothesis is true. Therefore, we accept it. However, it does not mean that this test and the large p-value have proven the null hypothesis. We'll take a look at why this is the case on the next slide. Why can't we say that the null hypothesis has been proven when the study isn't significant? Now, a study might not be significant because it doesn't have sufficient data. In this case, there isn't enough evidence to come to a conclusion. This scenario is often seen in court. Imagine that there's no evidence that exonerates the accused. That is, there's nothing that proves the person's innocence. However, there's also no evidence that the person is guilty. In this case, the person is acquitted due to a lack of evidence. This is according to the principle that every person accused of a crime is considered innocent until proven guilty. So a conclusion can't be drawn about this person's guilt or innocence. The same applies to the null hypothesis. If a study is not significant, that is, there's no credible evidence to show that the null hypothesis is false, we can't conclude that it's correct on this basis. To prevent another popular misunderstanding, the probability of the validity of the alternative hypothesis can't be calculated from the p-value for the null hypothesis. Just like the p-value doesn't specify the validity of the null hypothesis, the difference between 100% and the p-value doesn't equal the validity of the alternative hypothesis. So that rounds it off on statistical significance. In the last episode, you may have wondered about the 4 milliliter difference in the FEV1 value measured. If a study were statistically significant or not, it wouldn't say anything about the medical relevance of the results. If we'd measured a mean increase in the FEV1 value of 8 milliliters, then the study would have been significant. The next question to ask would have been whether this change is of medical relevance. Is it large enough that patients with asthma would really benefit from taking the drug? With a difference of 8 milliliters, which is less than 2% of the average adult's tidal volume, this question would have been quickly answered. This improvement certainly wouldn't make a difference to patients with asthma. Now, would you like to check if you've understood the most important information in this episode? Why not try the quiz on the next slide?